So let us now talk about uniqueness of splitting fields. So say we are given a field isomorphism var phi from f to f bar. So say you have a field isomorphism here var phi from f to f bar, and say you have a polynomial f of x which lies in this ring. So you have f of x here, and this gets mapped to f bar of x here. And let E be a splitting field for f of x, where f of x lies over this f. So the splitting field for this is this E. You can also write it as E of f to denote that splitting field for f. And for this f bar, you have the splitting field E bar. So this is the splitting field for f bar. You could also have written it like this: E bar subscript f bar. So denoting that this is splitting field of this polynomial f bar. And this again E bar over f bar be the splitting field for f bar of x. So where f bar of x has coefficients in this field f bar. So then you can extend this var phi to var phi tilde. So you can extend this to this. So this is a field isomorphism. You can extend it to this isomorphism. That basically means obviously this f is contained within this E, and this f bar is contained within E bar. So if you restrict this phi tilde to this field f, then you will just get this var phi back. So var phi tilde restricted to field f will just give you var phi. So that is the meaning of extension. Now this is called uniqueness of splitting fields, because if you take f bar equals to f, so in case you put f bar equals to f, then obviously if this is iso, our theorem is saying that this var phi tilde will also be iso. So these two splitting fields will be isomorphic to each other. So you have just unique splitting fields. So this is an important result, and for this result we are going to use a lot of material from this lecture, field monomorphisms. So you should see this lecture on field monomorphisms and understand it before you see this lecture. So first notice that this polynomial f of x gets mapped to f bar of x. Basically just the coefficients are changing. So if the coefficient here is something here is a1x, this say gets mapped to say something like a1 bar of x here. So first thing is that irreducible factors of f of x, they map to irreducible factors of f bar of x. So this we have shown in the lecture on field monomorphisms. So f of x looks something like this. So f of x, some bunch of linear factors x minus r1 times x minus r2 all the way to say x minus rm, and then multiply with some irreducible factors p1, p2, say all the way to ps. So the idea is that we should proceed by induction on the degree of f. So first the degree of f is 1. So this n is degree of our polynomial f. So this polynomial f. So for n equals to 1, everything is linear. So you just have these terms. You do not have these other irreducible factors. So f is already split in your field f. So within this f of x, this f is already split. Our polynomial is already split. It's just linear factors. So this f is equal to e. So this f and this e are equal to each other. So you have equality here. And similarly, this f bar will also split over this field f bar. So you have equality here also, because these linear factors will get mapped to linear factors in f bar. So this f bar also splits. So now you can set just this var phi tilde is just this var phi, because this isomorphism is precisely this isomorphism, because this f is equal to e, this f bar is equal to e bar for linear factors. There's nothing to be done. Now we use inductive hypothesis. So you assume that the theorem is true for degree of f less than n. So what does the theorem true mean? That is, we can extend this var phi to this var phi tilde if degree of f is less than n, and then we will come somehow to degree of f equals to n. So let p of x be irreducible factor of degree greater than 1 of f of x. So say this is our p. So p1 is our p. So this is an irreducible factor. It has degree greater than 1. It is not a linear factor like this. And this has a root a in our extension field. So correspondingly, you have another irreducible factor, which is p bar of x, which will be irreducible factor of f bar of x, and will have root b in e bar. So obviously this will have a root a in the splitting field of the polynomial, because in this field e, this f will have all its roots. So this irreducible polynomial also will have a root in e. So correspondingly, f bar will also have all its roots in e bar. That's pretty much it. So nothing new we have said, just using the definitions. Now from our lecture on field monomorphisms, we have already shown that if you have irreducible factors like this, px is right here and the corresponding factor p bar x is right here, then you can extend this var phi. This comes var phi comes right here, and this becomes phi here. So f of a, f of p. So you can extend this var phi to phi. So if this is an iso, this will extend to another isomorphism here. And where a is the root of the polynomial p of x and b is the root of p bar of x. So if you have this, you already have the roots of these polynomials. Now you can write f of x as x minus a times f1 of x. So say this was our polynomial to start with. This has a root, so you can write this as something like, say, x minus a times something, and then you take all these terms and all these terms, multiply them together and call it f1. So you can write it like this. F of x you can write like this, where a is the root of this polynomial p1, or our irreducible polynomial p here. Now correspondingly, you can take this f of x here to f bar of x right here, and this f bar of x, you have x minus p f1 bar of x. So this polynomial lies in this field, you adjoin x to it, and this polynomial lies in this field or over this field, you adjoin x to it. So that is, the coefficients here lie in this field f of a. The coefficients of f1 bar lie in the field f bar of p. So the coefficients of this, they lie in this field right here, and coefficients of f1 bar, they lie in this field right here. And it's kind of obvious, you have just gotten one field further because you wanted this x minus a, and you can only get this x minus a in f of a, because starting we had this polynomial p as irreducible. So you just want to take this factor out, and the reason you want to take this factor out is because you want to decrease the degree of f of x and f bar of x, so that you can use the induction hypothesis. Now what is the splitting field of f1? The splitting field of f1 will still be e. Its coefficients are in this field f of a, but its splitting field is still e, precisely because splitting field of f to start with is e, and f is x minus a times f of 1. Similarly, e bar f of b is the splitting field of f bar, so e bar over f of p, because coefficients of f bar are from f of p. Now we want to use the inductive step, so you can see degree of f1 and degree of f1 bar. So f1 and f1 bar is both less than n, because this is degree is n, this degree is n. If you divide by a term x minus a and x minus b here, the degree is going to be less than n. So since it is less than n, therefore you can use our inductive step. Therefore there is an isomorphism var phi tilde. So therefore there is an isomorphism var phi tilde, which will extend the isomorphism phi from f of a to f of p. So let us see this more pictorially. So you have this var phi, this is the isomorphism. You carry it to this phi, and you can carry this by our lecture in field monomorphism. So in that lecture you carried this var phi tilde to this phi, which was an iso, and this was true for an irreducible polynomial. In our case, we have taken this irreducible polynomial as a factor of f of x. So you can carry this further up using induction, because once you have a factor, then the degree has reduced, and therefore you can use the inductive step here. So the first step is just your field monomorphism lecture, second step is just your inductive step, and then you are done. So now we have shown the uniqueness of splitting fields, and this result is important. This will come useful later on in constructing Galois correspondence.